Machinery and equipment requirement in a precast factory. Let me start with a very important mindset shift. When people hear the word precast factory, they imagine a shed with some molds and concrete being poured. But that is not what a real precast factory is. A precast factory is more like a manufacturing plant, not a construction site. Just like an automobile factory has stamping, welding, painting, and assembly lines, a precast factory also has clear systems, clear machines, and clear flow. Every machine inside the factory exists for one reason only: to convert raw materials into finished concrete elements in a repeatable, predictable, and profitable way. That is why this slide shows a very simple idea: input, process, and output. Input means cement, aggregates, steel, water, admixtures. Process means mixing, casting, compacting, curing, and handling. Output means ready to install precast elements. If one machine in the chain is missing or wrongly selected, the entire factory efficiency collapses. So in this presentation, we are not just listing machines, we are understanding why each machine exists, where it fits in the process, and how all of them work together as one system, the production ecosystem. Now let's go one level deeper. A modern precast plant is not a collection of machines, it's a production ecosystem. Think of it like a cricket team. You don't win a match by having only one batsman or bowlers. Every role matters, and timing matters even more. That's why we divide the factory into 4 critical zones. Zone 1, planar or wall technology. This zone is where wall panels and vertical elements are produced. These are large surface elements, so accuracy, finish, and lifting safety are critical. Zone 2 is linear and slab technology. This zone focuses on slabs and long elements. Here production is continuous, fast, and volume driven. Zone 3 is the structural skeleton. This is where beams, columns, and load-bearing walls or members are produced. These elements carry the building, so strength and precision are non-negotiable. Zone 4 is plant logistics. This is the most underestimated zone. Cranes, movement systems, and handling equipment connect everything together. A factory fails not because machines are bad, but because these zones are not synchronized. When material intake, forming, curing, and dispatch are aligned, the factory runs smoothly, almost like clockwork. Battery molds. Now let's talk about one of the smartest space-saving systems in precast: battery molds. In many countries, especially in India, land is expensive and factory space is limited. So the question becomes, how do I produce more walls without increasing factory area? That's where battery molds come in. Instead of casting wall panels flat on the floor, battery molds allow you to cast multiple wall panels vertically inside a single compact frame. Gravity helps the concrete settle properly. Both faces of panel get a smooth finish, and multiple panels are produced at the same time. This system is ideal for solid walls, shear walls, and staircase walls. Another big advantage is productivity per square meter. Most battery molds dramatically increase output without increasing manpower or land size. In simple words, battery molds help you produce more using less space with better finish consistency. That is why they are widely used in high volume precast wall factories, the extruder. Now this slide is very important because this is where many people get confused. Most people think concrete becomes strong only because of vibration, but that is not true. An extruder works on a completely different principle: shear compaction. Here, the concrete is extremely dry, almost zero slump. You cannot pour it like normal concrete. Inside the machine, high-speed screws push this dry concrete through a shaped mold. As the concrete moves forward, it gets compressed under pressure and shear force. This vibration packs the particles so tightly that vibration is not required at all. The result is very dense concrete, high early strength, and very consistent dimensions. Extruders are mainly used for hollow core slabs, solid slabs, and sometimes wall panel. One very big advantage of extruders is cement saving. Because the concrete is compacted so efficiently, you need less cement to achieve the same strength. Also, the machine is self-propelling. It moves forward automatically as it extrudes the slab. This makes extruders ideal for high volume, repetitive products where speed, strength, and cost efficiency are critical. Now let's look at the slip former, which solves a different problem. Where extruders are great for standard products, factories often need flexibility. Different heights, different profiles, different product types. That's where slip formers come in. Slip formers work with slightly wetter concrete, and they use vibration instead of shear force. The machine slips forward slowly while the concrete is compacted inside the mold using vibration. Because of this, slip formers can produce a wide range of products like hollow core slabs, beams, lintels, foundation piles, gutters, etc. Another major advantage is the quick changeover. Molds can be changed faster compared to extruders, and maintenance access is easier. In many factories, a single operator can run the slip former, which reduces manpower dependency. So if your market demands variety more than just volume, slip formers offer a very balanced solution. In simple words, extruders is equal to speed and efficiency, and slip formers is flexibility and adaptability. Intelligent slabs. Now this slide talks about something very advanced, but the idea itself is actually very simple. Traditionally, a slab only does one job, carry load. But modern buildings demand more. They want faster installation, energy efficiency, and less on-site work. That's where intelligent slabs come in. In these slabs, systems like HVAC pipes, heating or cooling pipes, and insulation layers are integrated directly into the concrete during casting. So instead of installing these systems later at site, everything comes ready-made from the factory. So this gives three major benefits. First, huge time saving on site. Second, better energy performance because concrete's thermal mass is used efficiently. And third, cleaner and more accurate installation. These slabs are commonly used in commercial buildings, institutional projects, and energy efficient structures. This slide shows how precast is not just about speed anymore. It's about smart construction, the structural skeleton. Now we move to the core strength of any precast building. If walls and slabs are the skin and floor of a building, then beams and columns are the skeleton. These elements carry the load of the entire structure. So there is zero margin for error here. In a precast factory, beams and columns are cast in heavy-duty steel molds. These molds are adjustable, which means the same mold can be used for different sizes and cross-sections. Now comes a very important concept, pre-stressing. Concrete is very strong in compression, but very weak in tension. Pre-stressing solves this problem. High tensile steel strands are tensioned first, and then concrete is cast around them. Once the concrete gains strength, the tensile is released. This compresses the concrete internally, which allows the beam or slab to carry much higher loads with longer spans and less cracking. Columns can be cast vertically or horizontally, depending on the factory layout and handling systems. The key takeaway here is simple. Precast structural elements are engineered products, not just concrete shapes. Roofing solutions. Now let's talk about large span roofing, especially for industrial buildings and warehouses. In traditional construction, large spans mean more columns, and more columns mean less usable space. Precast solves this using special roofing elements. One of the most common elements is the double T slab. The shape looks like two T's joined together. This shape gives high strength with less material. Double T slabs can span up to 40 meters, which is extremely difficult to achieve with normal RCC. Another system shown here is omega and reverse omega profiles. These are specially designed for drainage, roofing efficiency, and structural stability. These elements are produced in adjustable molds, so slab thickness and web height can be changed easily. And what's the result? Faster roofing, fewer columns, lower foundation cost, faster project completion. That is why precast roofing is widely used in factories, warehouses, and logistics parks. Staircase molds. Now, this is a very practical problem on construction sites. Staircases are geometrically complex, labor intensive, and very sensitive to finishing quality. Casting staircases at site usually leads to dimensional errors, uneven risers, and poor finishing. Precast stair molds solves all of this. In a factory, staircases are cast in precision engineered molds. The entire staircase, including landings, risers, and treads, can be cast in a single pour. These molds allow adjustable riser height, adjustable step count, vertical or horizontal casting. Vertical casting saves space. Horizontal casting gives better surface finish. Once the staircase is demolded, it is ready to install at site with minimal work, of course, after curing. This not only improves quality, but also significantly improves the safety and speed at site. Boundary and retaining walls. Now let's move to a very common but very important application of precast. Compound walls, boundary walls, retaining walls. On site, these elements are usually built slowly, brick by brick or shutter by shutter. These consume time, labor, and space. In a precast factory, these walls are treated as standardized products. They are mostly cast vertically, which gives two big advantages. First, gravity helps the concrete compact naturally. And second, both faces of the wall get a uniform and smooth finish. Boundary walls are usually produced as panels, posts, columns, or integrated panel post system. Retaining walls are heavier and designed to resist soil pressure, so the molds are stronger and reinforcement is more detailed. Because these walls are repetitive in nature, precast production makes them faster, stronger, and more economical. This is why precast boundary walls and retaining walls are widely used in industrial posts, highways, infrastructure projects, large campuses. Vertical battery molds. This slide builds directly onto the previous one. Once wall demand increases, the next challenge is production speed. Flow casting has a limitation. You can only cast as many panels as your flow area allows. Battery molds break this limitation. By casting walls vertically, multiple panels are produced at the same time inside a single mold. This means less flow space, higher daily output, and better labor efficiency. Another important point is consistency. Since all the panels are cast inside the same mold system, dimensions, surface finish, and edge quality remain consistent across batches. Battery molds are especially useful when producing thousands of similar wall panels, and in simple terms, battery molds turn wall production from construction activity into an assembly line process. Now let's talk about one of the most important machines from a safety and quality point of view, the hydraulic tilting table. Large wall panels are heavy. If lifted wrongly, they can crack or even collapse. Hydraulic tilting tables solve this problem. The panel is cast horizontally, which allows easy placement of reinforcement, conduits, blackouts, and openings. Once the concrete gains strength, the table slowly tilts the panel into a vertical position. This ensures uniform stress distribution, no bending cracks, and safe lifting. Most tilting tables also have built-in vibration systems, which improve concrete density and surface finish. Because of this, tilting tables are commonly used for architectural walls, facade panels, and sandwich panels. They combine flexibility, precision, and safety in a single system. Let's talk about something that most people never see, but without which cities simply cannot function: drainage systems. On-site drains are usually cast manually, which leads to uneven slopes, leakage, and long construction time. Precast drainage systems solves all of these issues. In a factory, drainage elements are cast in precision steel molds. This ensures accurate slope, smooth internal surface, proper water flow. These drains are usually cast horizontally, which makes it easy to place reinforcement and control dimensions. Because the molds are reusable, the quality of every drain remains consistent. Precast drains are widely used in roads and highways, industrial layouts, residential townships, airports, and ports. The biggest advantage is simple. What takes weeks on site can be installed in a matter of hours. Now let's go a little deeper into drainage infrastructure. U-drains and box culverts are heavy-duty elements. They carry water, soil pressure, and sometimes even traffic load. So, precision here is not optional. These elements are produced in static steel molds designed for strength and repeatability. The molds allow accurate wall thickness, proper cover to the reinforcement, consistent cross-section. Depending on size, these molds can be horizontally cast or vertically cast. Small U-drains are produced in large numbers. Large box culverts are produced with fewer cycles but higher weight. Precast culverts are commonly used in highways, railways, industrial drainage, flood control systems, etc. Factory casting ensures that every unit meets structural and durability requirements. Now this slide shows a very powerful production method, slip forming for infrastructural elements. When demand is high and elements are repetitive, stopping and starting molds become inefficient. Slip forming solves this by enabling continuous production. Concrete is continuously fed into the mold. The machine moves forward slowly, while the vibration compacts the concrete. As the section exits the mold, it already has enough strength to hold its shape. This method is commonly used for U-drains, barriers, channels, linear infrastructure elements. The biggest advantage here is speed. Instead of producing one element per cycle, you produce meters of product continuously. This makes slip forming ideal for large infrastructure and government projects. Now let's talk about something that works silently underground, but without it, no city can function. Pipes and inspection chambers. These elements are the hidden network of infrastructure. If pipes are weak, misaligned, or leaking, the entire system fails. In precast production, pipes and chambers are cast in precision control molds. Most pipes are cast vertically because this gives better circular accuracy and a smooth internal surface. Inspection chambers are produced as modular units, which can be assembled easily at site. This modular approach ensures faster installation, better alignment, and long-term durability. Precast pipes and chambers are widely used in the sewer system, stormwater networks, and industrial drainage. Factory casting ensures every unit meets hydraulic and structural performance requirements. If you ask what the most important system in a precast factory is, the answer is simple: the batching plant. Every product depends on the quality of concrete, and the concrete quality depends on accurate batching. In precast production, especially dry cast, even a small moisture variation can cause major problems. That's why batching systems are highly controlled. They manage cement quantity, aggregate grading, moisture correction, and admixture dosing. Planetary mixers are commonly used because they can mix very dry concrete uniformly. The batching plant sets the production rhythm of the factory. If the batching stops, everything stops. That's why this system is often called the heartbeat of precast plant. Now let's talk about something many people underestimate: handling and lifting. Precast elements are strong, but only when handled correctly. Wrong lifting can introduce micro cracks that are invisible today but dangerous later. That's why precast factories use spreader beams, lifting anchors, and controlled rigging systems. Spreader beams distribute the load evenly and prevent bending stress. Lifting anchors are designed and placed based on element weight and geometry. All handling follows a planned lifting sequence. This ensures safety of workers, protection of element, and zero damage during movement. In precast, handling is not an afterthought. It is part of the engineering design. Now that concrete is mixed perfectly, the next question is simple: how do we deliver this concrete to the mold without losing time or quality? That is where concrete distribution systems come in. In a precast factory, concrete cannot wait. If it starts setting before reaching the mold, the entire batch is wasted. That's why factories use controlled systems like flying buckets, conveyors, speedy concrete distributors. These systems ensure fast delivery, uniform supply, and minimum segregation. In automated plants, concrete is delivered exactly when it is needed. This improves productivity, surface finish, consistency between elements. Concrete distribution may look simple, but it directly affects the cycle time and quality. Now this slide is where everything comes together. A successful precast factory is not built randomly. It is designed backward from the final product. Raw materials come in from one end, and finished elements go out from the other. In between, every system is connected. Batching plant feeds production lines feed curing areas feed storage yards, cranes and logistics connect everything. When this layout is planned properly, material movement is reduced, waiting time is minimized, and labor efficiency is increased. This slide shows that precast is not just about machines, it's about flow, planning, and integration. That is what turns a factory from a cost center to a profit engine. Now let's talk about muscle of the factory, cranes. Precast elements are heavy. Some weigh a few tons, some weigh tens of tons. To move them safely, factory use overhead cranes inside sheds, gantry cranes in open yards. Overhead cranes handle demolding, internal movement, and mold handling. Gantry cranes handle storage, loading, dispatch. These cranes are designed with safety interlocks, load sensors, and smooth movement controls. Good crane planning improves safety, speed, and element life. In precast, cranes are not optional, they are part of the production system. Now let's simplify a very common confusion. Extruder versus slip former, which one is better? The answer is it depends on your product and market. Extruders use very dry concrete, compact using shear force, are very fast, save cement, and best for standard and high volume products. Slip formers use slightly wetter concrete, compact using vibration, and offer more flexibility and supports multiple product types. So the real question is not which machine is better, the real question is what does my market need every single day? The correct machine choice decides profitability more than anything else. Now let's step back and look at the bigger picture. Precast construction is not just a technology shift, it's a mindset shift. From site-based construction to factory-based manufacturing. From unpredictable outcomes to controlled, repeatable results. From labor dependency to process dependency. When machines, layout, and systems are aligned, quality improves, speed increases, and cost becomes predictable. This is why precast is growing rapidly across residential, commercial, and infrastructure projects. This is not the future anymore. This is the present of construction.